Now we need to understand those. Now, rutting first. What is rutting? Longitudinal depressions in the wheel paths accompanied by a small upheavals. So if you look at, this is a traditional picture. When you talk about rutting, this is if you Google search rutting, you will see this particular picture. Tom Harmon, my supervisor, was telling me they took this picture. This was constructed, and a week or so later, I think, this happened on this particular road. This was a pure bad design. So if you do a bad design, this is what happens in a week. Okay, the bad design. We're going to talk about that tomorrow. But bad design could be as simple as you did not account for the traffic level. That's it. Your structure might be perfect, your materials might be meeting the Superpave specification, but if you use the wrong end design or design gyrations, we're going to see this afternoon, for that particular road, you might just get this. Okay, so it's, pavement design is traffic, climate, and material properties combined all together. Now, what you're seeing here is a tire load. So we're going to have this actually, the software I sent you yesterday, is a layered elastic code that will allow you to see this with a certain truck load. And we're going to do this exercise tomorrow. Believe me, you're going to see how simple it is to get a strain distribution on a pavement like this. So we're going to talk about that tomorrow. Now we have a tire load. What you're seeing is a tensile strain and compressive strain here. This tensile strain causes top-down cracking. This tensile strain at the bottom causes bottom-up cracking. Sometimes they say that it's meet me in the middle cracking. So sometimes, it starts from the bottom, the top, and it meets in the middle, kind of a thing. And rutting is usually caused by the vertical strain below the tire. Now we need to consider that in Superpave binder specification. Now, fatigue cracking. Fatigue cracking is because of too many repetitions of heavy load, inadequate support. If you don't have enough strong enough or high CBR or high modulus subgrade or base. If you have a brittle binder at the bottom of the asphalt, if you have poor drainage, all these things can cause fatigue cracking, top down or bottom up. And mostly we are talking about bottom up fatigue cracking here. Low temperature cracking is because of the temperature fluctuations. You have transverse cracking. So contractions during the cooling induces tensile stresses. You have contraction, expansion because of the daily and seasonal variations of temperature. And when the thermally induced stresses are well in excess of the material strength, then we have thermal cracking, thermal snapping. And so the pavement Superpave guide or Superpave binder specification attempts to consider rutting, fatigue cracking, and thermal cracking. But the Superpave, as I said, I'm underlining the word I'm saying, Superpave design, it attempts to consider these three. This is great. Doesn't mean that if you have a perfect Superpave spec, it will perform perfectly, because we have aggregates in there. Properties of the aggregates play a significant role. So you need to think this as from small to large to larger scale. So let's see, so if we again look at this at multi-scale. So now I'm going backwards. So we are starting, I'm going to go backwards. Let's say we have a pavement structure. We have AC1, AC2, and AC3, and base, let's say, and subgrade. This is the scale number 1. So if you take a look at an area and expand it, we're going to have aggregates. We're going to have aggregates. You're going to have binder, So this is the mixture scale, scale 2. Mixture or HMA, even though nowadays we have warm mix asphalt, but this is structure. So we have the tire here. And then if you look into scale 3, binder scale. So what we are doing right now is we started with scale 3. So we are trying to address the rutting, fatigue cracking, and thermal cracking from scale 3. In the afternoon, we're going to talk about how do we do that at scale 2. And tomorrow, we're going to talk about how we're going to do that in scale 1. Okay? So the fact that you have like a perfect Superpave, if you can't see my hands, let me know. Okay. So this is actually Superpave PG spec. So Superpave binder specification. This is Superpave mix design. So, and then we have structural design. So this is where we are right now, and we try to talk about rutting, fatigue, and thermal at this level. Any questions at this stage? Yes. Yeah. No, that's also tensile. So, yes, both tensile. And the software that we're going to run tomorrow, we will see the tensile strain on the top. We're going to compute it, and we're going to see the tensile strain at the bottom. We're going to see both of them tomorrow, hopefully. Any other? The compressive is only for rutting. All right. Now, these are the forms of failure that we are trying to address. And then, in addition to those, we have shoving, bleeding, raveling, and we have a whole bunch of other problems also. But these are the main things that we consider in Superpave mixture design. Superpave binder design. So now the goal for the binder at scale 3 that I mentioned is we want a specification to determine what materials will provide acceptable performance against these modes of failure. That's the whole goal of the Superpave specification. So in addition to that, what other concerns should the specification address? Constructability and safety. Now I'm going to ask one question to you. Somebody comes up with an new asphalt binder made of swine manure, which, by the way, there is North Carolina A&T University have been working on it quite a while, swine manure. And they presented this work in one of the Transportation Research Board conferences. And one of the very, very experienced binder manufacturer and, very well respected binder guy, let's say, asked a whole bunch of questions. Like, he listed 8 different possible questions. So I want you to guess one or two here. So I will give you like 10 seconds to think about this. Okay, 10 seconds is over. All right. Who I did not ask. I can't see your name. I'm sorry, Mike, right? Yeah. Okay. What would be a problem with this binder made with a swine manure? Smell. It's logical. So if it smells, you know, it smells, then you're going to get complaints from departments of environmental quality. And they're going to see complaints from environment. So there are many different, I'm not going to go on this, but there are many things. One of them was, how about cleaning of the trucks, right? You know, you put this swine manure based binder, and then those truck needs to be cleaned. And what kind of fluid do you need? In asphalt, we know orange cleaner. It's very, you know, everybody, it's cheap nowadays. You know how to clean. Now, if anytime you introduce a new material, you have a whole bunch of problems. So one of the things about asphalt binder is it's a great material that satisfies a lot of needs. And when you come up with a new material, you get a whole bunch of different issues with it. Now, two different issues with asphalt binder, though, that we don't want it to happen is safety and constructability. So asphalt binders being a petroleum product, it can potentially catch fire, so we don't want that. So we have a testing for that. And also, asphalt binder being a viscoelastic material that changes properties with temperature, it might be too stiff. You may not be able to pump through the pipes, you know, if it is too stiff. And that's called constructability that we have to satisfy. Now, original strategic highway research sharp objective was modify the asphalt chemical specification for asphalt. So as sharp researchers, they wanted okay, here's the recipe for chemistry of asphalt, and use that. And then they probably came across this. If you put a spoonful of wine in a barrel full of sewage, you get sewage. If you put a spoon of sewage in a barrel of wine, you get sewage. You know, chemical concentration is not necessarily the key. What you get at the end is the important thing. So the property of the material at the end. So that's what they decided. So they said, okay, we don't care how you add, what you add into the material, but at the end, we want a performance-related specification based on physical characteristics of the binders. Now, one thing that we know is, are the properties of asphalt binders constant over a pavement's performance life? That's one of the issues about binder. You know, like swine manure, it has a smell. Asphalt, it ages with time. It changes property with time. It's, you know, it's a lot more comfortable. That's why I said my student, and this is asphalt mixture, is soil mechanics and steroids, but this steroids is really, really weird material. If you leave an asphalt binder in a room, tested 10 minutes after you leave it on the desk, tested 20 minutes after you leave it on the desk, you will see different properties. Binder doesn't age in that 10 minutes. There's a different mechanism that happens. Temperature hardening, that happens at the temperature. That's why when you look at the specification of binder testing, there are clear guidelines on when to test and what time to, what strain level to test. And those are extremely important because we are simplifying a nonlinear viscoelastic material into a simple case. So the point I'm trying to make is asphalt binder is complicated. We have to follow the specification very carefully to test it. Now, asphalt binders property does change with time.